Hey, good afternoon, everybody. So today the plan is to go over Minitab and teach you how to use Minitab for inferential statistics. You know how to use it for descriptive statistics. This part could be useful for your project. It doesn't mean that you have to use Minitab. You can use any software that you like, R, MATLAB, MathCAD, Mathematica, anything for statistical analysis. But if you want to use Minitab, I'll teach you how to do some statistical inferences that we learned in this class, starting with the very simple one, which is hypothesis testing and confidence interval for the mean of one population. Let's start with that one. Let's say we have a sample and with 9 observations, and we want to perform this hypothesis testing, whether mu is equal to 5 or mu is not 5. By the way, how many of you have used Minitab before? I asked this question. Okay, good. So basic statistics. Now it's acting up. Really? Okay. Basic statistics, one sample Z, because we'll start with the case that sigma is known. Honestly, I don't remember what sigma is, but let's say sigma is 0.1 for this example. Or maybe I can cheat a little bit. See what sigma is. It's 0.2 actually. So let's say we know sigma is 0.2, therefore we can use one sample Z. And again, that's the basically path. Basic statistics, one sample Z. And we put all data in one column. Which column is that? C1. Double click. What is the standard deviation? It's 0.2. We want to perform hypothesis testing. And what is mu0? Here in this case is 5. And if you want, you can have some graphs like histogram, individual plot, box plot. I select all of them. And this is basically your confidence level, alpha, 95% in this case. And this is your alternative hypothesis testing. It is two-sided or one-sided. One-sided less than, one-sided greater than, it's inequality. Okay, I'll go with this one. And okay. Now let me start with the session. It has some useful information. So as you can see, mu is equal to 5 versus mu is not equal to 5. This is mean. This is sample average, sample standard deviation. What is this guy? Anybody can remember? Standard error of mean. What is it? Standard deviation of? Sample. Which is? Sigma divided by the square root of n. That's sigma divided by the square root of n. This is the confidence interval that we have. Based on the confidence interval, we know that 5 belongs to this, does not belong to this confidence interval. Therefore, we need to reject h null. Okay? Because 5 is greater than upper bound. This is the Z statistic, which is, I'm sure you all know how to calculate it by now. But this is Z statistic, which is negative 3.17. And this is the p-value corresponding to this test. And p-value is less than 0.05. We reject H null. If you want to use Z, you need to compare it with Z alpha over 2. And in this case, is Z of 0.025, which is 1.96. And again, you get the same basically answer. You need to basically compare the absolute value of this Z. Any questions so far? You good? So as you can see, this is box plot of data. This is where your hypothesis is. It's 5. And this is your confidence interval. So your hypothesis is far from your confidence interval. You reject H null. Does it make sense? Same conclusion if you use dot plot. Again, just different way of showing the data, or histogram. It's not a very good histogram because you only have 9 observations anyways. Histogram is not a good tool for analyzing this data. Any questions? Are you good? So what if we don't know variance? Stat, basic statistics, 1 sample T. Okay? Then, again, C1 is the value, hypothesis testing. 5, I just use dot plot or individual value plots. And option is the same. You can see. And then OK. So your confidence interval is a little bit wider, as you can see, because we are estimating the standard deviation. Is it always the case? No. Definitely not. Sometimes it could be wider, could be tighter. But again, in this case, again, we reject H null because H null is far from your confidence interval. Any questions? Is it clear? OK. How about 2 sample T or 2 sample Z? Stat, again, basic statistics. This is 2 sample T. Why I don't see any 2 sample Z? That's interesting. Okay. They don't have any 2 samples Z. I don't know why. But I guess in reality, it doesn't really matter. You don't know the variance, so 2 sample T is more useful. So 2 sample T, let's say we have 2 population, mat A, mat B, and we want to compare these 2 population in terms of average, if they are equal or not. So 2 sample T, then samples and ID. So since you have each sample in 1 column, you select the second option. Sample 1 is in column 2, as sample 2 is in column 3. Okay? There is another way of entering data. If you have all samples in 1 column, in this case, what you have is something like that. So you have all numbers here, let's say 13.2 all the way down until 13.3. Then 14 is the first one, then 13.6. So you have a code here or population number. So you put 1, 1, 1 here up to here, which means population 1, and then 2, 2 here, which means population 2. That's another way. So your samples, in this case, would be this guy, and your ID is this guy. Anyways, or you can have a summary of data. So for example, what is sample size for the first one? What is sample size for the second one? What is the x bar 1? What is x bar 2? What is s bar 1 squared? What is s bar 2 squared? You just summarize the data and put it here. So there are 3 ways of entering the data. Okay? So I use this one. Again, if you want to basically have different alpha, you can change it here. The hypothesis that we are doing right now is mu1 minus mu2 is equal to mu d, or some number. And you can define that delta or mu d here, right now is 0, which means whether these 2 are different or not. Okay? And we can change the alternative. So here, assume equal variances. Do you remember? If the variances are equal, then you push this button. In general, if the variances are not equal, you uncheck this one. What should you do in your project? First, you need, if you want to do two-sample T, first you need to check whether variances are equal or not using the variance hypothesis testing. If they are equal, when you are performing this test, you check this option. Otherwise, you don't check it. Okay? Does it make sense? Okay, then let's have a box plot this time. And then okay. So as you can see, this is the box plot. This is the average of Math B. This is the average of Math A. And here is the basically report. So sample mean, sample standard deviation for first population, the second population, and these are the standard error, which is S1 squared divided by the square root of 10. Okay? This is not estimator for variance. What we are using for estimating the variance is pooled estimator. Okay? So here it is, 95% confidence interval. It includes 0. Therefore, we cannot reject H null. They are equal. Okay? This is the t value, and this is the p value corresponding to that. You remember the degrees of freedom, n1 plus n2 minus 2. So why this is 17, I have no idea. Did I check that option or not? Oops. Oh, no. Sorry. Yep, that makes more sense. Okay. So n1 plus n2 minus 2, which is 18. And that was for the case that variances are not equal. Okay. The other one here. So the degrees of freedom, you remember, is very weird degrees of freedom, which is the combination of S1 and S2. Okay, any question? Is it clear? Pool standard estimator, remember? You pull them together and the sort of like weighted average. We good? So let's see. Pair T. When you have dependency between two samples, okay? So let's say, for this example, let's assume Math A is the math score of students before training, and Math B, let's say B is before, and Math A is the math score after training. So since we are using the same students, they are not independent. We need to use pair T. And you remember pair T, you subtract the first population from the second population, and you get one data. So pair T, so very sample 1 is Math A, very sample B, Math B. And again, the same thing, push OK. There is no inequality or equality assumption for variances, because when you subtract, you only have one population. So as you can see, this is some statistics for first population, second population, and this is the statistics for the difference, okay, which is each minus the other one. This guy minus this guy, this guy minus this guy, okay? This is confidence interval. It doesn't include 0, which means that those two populations are not the same. So can you see the difference? If you assume they are independent, there is no evidence for rejecting H null, which means the means are same. But if they are dependent, if you do basically pair T, you can see the means are different. You reject H null. Okay? Any questions? You good? Yep. So let's say these two are independent. Then we should not use pair T. And we use like two sample T. and there was no evidence for rejecting H null, which means these two populations means are the same. Okay. However, if they are dependent, you need to use pair T, and then as you can see, the equivalency of the means is rejected. They are not equal anymore. So that dependency is very important in your analysis. That it has a severe effect on your analysis. Okay. Any questions? We good? So, stat again, basic statistics. For proportions, you mean P1, P2 for binomial distribution, or it's not the same. Okay? Or in general, you can say P1 minus P2 is some delta. It's not that delta. You can do hypothesis testing. I skip one proportion because it's simple. For two proportions, this time I'm going to use summarized data. I say sample 1 is, 100. This is the sample size. And how many of them are events? I would say, let's say 5. And then sample 2 is 200. Let's say 8 of them are event. So this is first population. This is second population. I want to see whether their difference is 0 or not. Okay? Here. Again, you can change that difference if you want. So you have two methods for estimation. One is estimate the proportion separately or use the pooled estimate. Do you remember? Your P bar was, see who can remember. Nobody? X1 plus X2, N1 plus N2. So that's the pool estimate. Okay? The other one is estimate for each of them separately. Estimate P hat 1 and P hat 2. I don't like this method. I think this method, this is more accurate method. So always go with, basically use the pooled estimate of the proportion. This guy. Okay? If you want to do hypothesis testing, if you don't want to do hypothesis testing, then you can use, if you want to just do confidence interval, there is no hypothesis testing. You can use this guy, estimate the proportion separately, which is basically, so you have your P hat 1, which is X1 divided by N1, and you have P hat 2, which is X2 divided by N2, and the variance would be this is for confidence interval. No hypothesis testing involved. Okay? If you are using for hypothesis testing, this is the P that you need to use. So again, this is for confidence interval. This is for hypothesis testing. Confidence interval, hypothesis testing. I go with this one because I'm doing hypothesis testing. And then, okay. So as you can see, 0.05 is the estimate for the first population, 0.04 for the second population. The confidence interval includes 0. I cannot reject H null. They are the same. And this guy here, oh, by the way, that's very interesting. So this is the p-value when you use central limit theorem, okay, and you approximate it with z distribution. This is for, guys, can you see it or not? Maybe I can. I don't know how I can make it larger. Do you have any zoom? No. I don't know how I can zoom in. Yeah, but there is another screen back there. If you are sitting back there, you can look at that screen. Anyways, so you have one p-value which is 0.688, and this is the regular p-value when you are approximating your test statistics with standard normal. And if you want to use binomial distribution, I haven't covered this basically test in class. So there is one exact test based on binomial distribution. You can use that one, and that would be 0.766. When you have large sample, these two should be very close. Okay? Any questions? Okay. Good. Again, you can have test for Poisson rate, okay? And for variances, if you have two variances, you can have the test for that two variances. Let's see, we want to see if the variance of population 1 and population 2 are the same. Again, options. So that's the ratio. So your H null is sigma 1 squared divided by sigma 2 squared is 1. And your H alternative is or you can have a lambda here. It's not lambda. Okay? And this one is the lambda. Okay. So if you want to test a standard deviation, you select this one. If you want to test variance, you select this one. I'm testing variance here. And so use test, if you want to approximate it based on normal distribution, you select that one. If you have large sample, you can do that. Otherwise, you cannot. So what you learned in this class was based on what? Was based on F distribution. So do not select this one. Okay? Or for one, basically sigma was based on chi-square. Okay? Select this one, graph. You can have a summary plot. Let's have this one. And result, if you want basically to save any part of results in that spreadsheet, you can basically select it here. So as you can see, okay, this is the hypothesis that we are testing, as you can see, whether ratio is 1 or not. This is the confidence interval for the first population, confidence interval for the variance of the second population. Those confidence interval are obtained based on which distribution? Do you remember? These individual confidence intervals. Anybody? What? Chi-square distribution. Because this is just the confidence interval for the variance of one population, which is based on chi-square. So this is chi-square, this is chi-square. Okay? And so this is the ratio of a standard deviation. This is the ratio of the variances. So basically, this is S1 squared divided by S2 squared. That's what it means. For the other one is S1 divided by S2. And so there are two methods. One is Bonnet and the other one is Levine. The one that we're using in this class, based on the F distribution, why we have one? Is actually neither. That's very interesting. Yeah. We are not, they don't have that F distribution here. Let me see. Or maybe I'm making a mistake. Yes. Just give me a second. Yes. Yeah. I made a mistake. So let me rephrase what I said. Let me go back. Okay, here, when you go to options, this one, I said this is based on the large sample. No, this is not. This is based on the assumption that observations are coming from a normal distribution, which is the most important assumption for doing hypothesis testing for basically variances. So you remember the first assumption that we have, X follows a normal distribution. If X follows a normal distribution, then you can claim that S1 squared divided by S2 squared under-dimensional follows a F distribution, an F distribution. You remember that? So if this assumption is valid, if observations follow a normal distribution, you check that option, okay? Check mark this, and then push OK. And what happens is this one. So that's the F-test that we know of. This is the confidence interval for the standard deviation, and this is the confidence interval for variances. Okay? We know how to calculate the confidence interval for variance. How we can calculate confidence interval for a standard deviation? How? For variance, we know that it's coming from F distribution. How about the standard deviations? What? Just take a square root, exactly. Take a square root of the lower bound and upper bound, you get the confidence interval for standard deviation. Okay? And this is the test statistics, and this is p-value. P-value is greater than 0.05. We cannot reject, therefore, sigma 1 squared divided by sigma 2 squared are the same. If that normality assumption is not valid, then we basically use some non-parametric test here, which we haven't covered in class. But anyways, you can interpret it like regular p-values. If it is less than 0.05, then we reject the null, otherwise we don't. Any questions? You good? And I think the plot that we had here, I can find it again. No, it's not this one. So this is the box plot. This is basically confidence interval based on chi-square distribution. And this is the confidence interval for the ratio. And since 1, you can see, number 1 belongs to this confidence interval, therefore we do not reject H null. And confidence interval is not symmetric, because F distribution is not symmetric. Any questions? We good? Again, if normal distribution is valid, check, select that option, and then you do basically F-test, like this. Okay. So what else? We are done with hypothesis testing. Not the variances, individual observations. Yes. And basically, I'm going to tell you how to use normality test for that. So normality test tells basically, because we know that like most of methods that we are using are based on the normality assumption. Okay? Especially for the variances, inference for variances. For mean, not really. Why? Because based on central limit theorem, if you have large sample, then it should be fine. X bar follows a normal distribution, even if X doesn't follow a normal distribution. But for variances, yes, this is very sensitive. We need to check that. So let me go with normality test first. So let's see. We have a value, let's say mat A. We want to see if it's coming from a normal distribution or not. This is the most famous. You remember we had a chi-square test in class, but in practice they use some other test which is different from the chi-square test that we introduced in class, goodness of fit. That test is called Anderson-Darling. That's the, I would say, the most popular one, Anderson-Darling. And then it's like this one. You can see it gives you a normal probability plot. If data are basically along this line, this is a straight line, we can say they follow a normal distribution. Hopefully, I'll go over normal probability plot, what is the principle behind that, and how to plot it by hand on Wednesday. But anyways, so your p-value here is 0.7. So basically, H null is X follows a normal distribution. H alternative is not. Here, p-value is not less than 0.05. We cannot reject H null. Data follow a normal distribution, as you can see. That makes sense because they are along this line. They are scattered along these lines, this straight line. Any questions? We good? Yes.
Darling test?
Yes, this is Anderson-Darling test. That AD is the test statistic. You remember, for example, for mean, we have Z as test statistic. This one is called AD, Anderson-Darling test. But you need to basically interpret the p-value. And this one, your x-axis is the actual value, and your y-axis is basically the value corresponding to normal distribution. Okay? So if these values are similar, then I can say they're coming from normal distribution. Okay? I'll show you on Wednesday how to do normal probability plot. What is the principle behind that? And any questions? You good? Histogram is just a visual, actually. So you cannot do any inference.
I meant just like right now to show.
Oh, yeah. Okay, yeah, sure. Graph, histogram with fit, math A. Okay. Not good. We can change the number of innings. So 8 is a lot because you have only 9 or 10. So let's make it 4. It's better. But honestly, with 10 data point, histogram is not a good tool. For histogram, if you want to have a good histogram, informative histogram, you need to have at least 30, 50 data points. Okay. Yeah. Actually, Anderson-Darling is fine with a small number of samples. And actually, I think it's not very good when you have very large number of samples. Let's say you have 500. Anderson-Darling tends to not to reject basically your H null. That's one of the problems that Anderson-Darling has. Okay, so that's for this. So let's say we want to test the correlation between two variables. So correlation between mat A and mat B. We want to find the correlation coefficient and do the hypothesis testing. You remember in the regression lecture notes, two variables, what is the correlation coefficient, and the hypothesis testing was what? Whether this is rho actually is 0 or that rho is not 0. Okay? It should be not 0. Okay? As you can see, the correlation between these two variables is 0.988, and the p-value is 0, which means they are really correlated. And now you can see why we need to do paired tests here, because these two are not independent samples. Okay? Any questions? You good? Yes. That's a good point. So what if your data is not normal? So one thing you can do, if you are doing something which requires normality, like ANOVA or regression, if you are doing hypothesis testing for mu, that should be fine. But especially when your sample size is large. What you can do is something called, let's see if I have it here. No, but we have it here on the control chart. Box-Cox transformation. So that Box-Cox transformation, what it does is basically try to find a power transformation. So let's say y follows a distribution that you don't know what it is. It tries to find a power transformation, or let's call this lambda, such that z follows a normal distribution. Okay? So you select your number, for example, here, values, and then your subgroup size is 1. And here, you can say this is find the optimal value. You always use that. And if you want, you can store your z values here after transformation in one of the columns. Let's say C5. You can see this is the optimal lambda. Okay? Optimal lambda means the one that basically makes the data more normal. Let's call it. And this is basically your transform data. Okay? Yes?
Does that give you some sort of information about what the actual distribution is?
That's a good point, actually, yes. If you're using log, I mean, sometimes instead of like direct power, it uses log, then your distribution probably is exponential. So there are some basically relationship. In the Montgomery book, it has a table, say, for example, Poisson probably is this relationship, exponential is this relationship. You can basically trace back and say, okay, this is the optimal lambda, probably it follows this distribution. Speaking of that, if you want to find which distribution it is, there is a tool. Let's say you want to see if it's coming from an exponential distribution or not. I'm running out of time. I need to be basically hurry up. So you can use probability plot. So probability plot, again, graph, probability plot. This is single. You use your graph variables, let's say values, and then you can find distribution. There is a list of distribution that you can select. For example, you can say variable, gamma distribution, log normal distribution, anything that you want. Okay? Exponential distribution. Then you see it's definitely not exponential distribution. And the p-value is based on Anderson-Darling. Okay? Make sense? Okay. Now, the next topic is analysis of variance. And we have two types of analysis of variance, actually three types. One is one-way, two-way with blocking, two-way with interaction. So let's start with one-way. Let's say we have three different glass type. So our factor is this, and the response is light output. And we want to see if the light output for glass type 1 is the same as glass type 2, same as glass type 3, and your H alternative is otherwise. Okay? For a moment, assume that temperature is not here. Just one-way ANOVA. Stat, ANOVA. Forget about this one-way. Always go general linear model. General linear model, it's good for ANOVA one-way, ANOVA two-way, ANOVA with interaction. Select that one. So what is your response? Is light output. What is the factors that you are interested in? Is glass type. Okay? Then okay. So here is the output. You can see that's the treatment. with 2 degrees of freedom because we have only 3 levels. And this is error, this is total, this is ANOVA table. Okay? This is basically your SS, this is your MS, mean square error, this is your F value, P value, which says it's not basically significant, which means basically your mu1 and mu2 and mu3 are equal. We cannot reject that H null. Okay? Any questions? Is it clear? Now, let's say we want to use the same setting for regression. Okay? So I want to predict y as a function of x, but my x is categorical and my y is continuous. We know that we can use either ANOVA or regression with dummy variables, if you remember. Okay? So we have 3 factors, so we need to have 2 dummy variables. So how can I do that? If I go to coding here, I change coding to 0 and 1, which is basically dummy variable, and I say my reference level is the first level because I have 3 different glass types. And I say, okay, okay. And here is the equation I get. So as you can see, for dummy variables, this is the equation. We have D1 and D2. Okay? So if D1 and D2 is 0, this is glass type 1. For glass type 2, I think this one is 1, this one is 0, and for glass type 3 is this scenario. Okay? So forget about this part because the coefficient for this part is 0. So I just erase that. So this is the equation. If it is glass type 1, then this would be 0, this would be 0, and your prediction is this guy. If it is glass type 2, then I replace glass type 2 with 1. 1 times 48, and this one would be 0. If it is glass type 3, this is going to be 0, this one should be 1. Does it make sense? Okay? Any questions? We good? Now, what if I want to have 2 factors with blocking, no interactions? Okay? So what should I do? I select this, I go to model. This includes interaction. If I don't want to have interaction, it says like, what is the order of the model? So interaction order 1 means there is no interaction. This means one of the factors is block. Okay? There is no interaction. Okay? And then okay. Here, as you can see, this is the analysis of variance. Temperature, glass type. Forget about lack of fit. I will explain what lack of fit is. Let me just erase this part. It's easier to understand. So temperature is the factor that you are interested in. Glass type is blocking. Or it could be the other way around. Your glass type is the factor you are interested in. Temperature is the block. And you have the p-values. So both of them are important factors. Make sense? If you want to have interaction, in model, you select 2. So it gives you the interaction as well. Okay. And that's what you see. So with interaction is right here. Again, let me just erase this part. This is more related to regression. When I talk about regression, I explain what lack of fit is. So as you can see, Why it doesn't have interaction? Interesting. I selected. Okay. Sometimes it's very strange. Should have given me the interaction. I don't know why it does not give me interaction. Maybe she doesn't like it. Okay. So I will figure it out for Wednesday. But before that, let me show you how to validate the assumptions. So graphs. Do you remember the assumptions that we have in ANOVA? Normality, constant variance, independency. So 4 in 1 gives you all 4 plots in one basically graph. And here it is. So you can see in this case, not really, none of assumptions are valid. So not normal, variance is not, and definitely it's not random order. You can see that? So if you want, you can basically run that Box-Cox transformation to see if it helps. I'm not sure. I'm trying to see if it helps or not. So I can basically select this slide output and subgroup size 1. Let's have it in C5. Okay. Okay. As you can see, rounded value is 1, which means it didn't help at all. Because everything to the power of 1 is actually doesn't help. So Box-Cox transformation sometimes helps, sometimes it doesn't. In your project, when you have non-normal data, you can use that one. If it helps, it's good. Otherwise, just write it down. Normality assumption is not correct, so we cannot do it this way. I'm going to continue with Minitab to teach you how to do regression and also check the variance. You know how to check normality, but the assumption of whether variances for 3 populations are the same or not, I'll teach you that on Wednesday. Okay? Any questions? Good.
For different distributions in this bit.
But yeah, you can. But let's say your distribution is exponential. What do you want to do? There is no ANOVA for exponential distribution. There is some ANOVA for non-parametric ANOVA which doesn't require basically normality. This is called Kruskal-Wallis, but this is non-parametric test. For this class, we just require